Welcome to Matrix Algebra 101, Part 3, part of the TLR course. Just a reminder, in Part 2, we looked at some calculations, addition, subtraction, and multiplication of matrices. In Part 3, we are going to look at one special type of matrix, but also some other calculations in matrices and also linear dependency and rank of matrices. So welcome then to part 3. An identity matrix is basically a square matrix, but it is also a special type of square matrix, a diagonal square matrix. You will remember from other parts of this course, we have talked about a square matrix being a matrix with an equal number of rows and columns. And we have also spoken about a diagonal matrix being a matrix that is a matrix with only elements on the diagonal, elements on the diagonal, and on the off diagonals we have zeros. So an identity matrix is a very special type of diagonal matrix with a ones on the diagonal and obviously zeros on the off diagonal. So I2 in this case is an example of a 2 by 2, 2 rows, 2 columns identity matrix, and I3 in this example is a 3 by 3, ones on the diagonal, 3 rows, 3 columns, and ones on the diagonal. So an identity matrix has a unique talent, as they call it here. Any matrix, doesn't matter which matrix, can be pre-multiplied or post-multiplied by its own identity matrix, and it will give you the same matrix. In normal algebra, it's like multiplication with 1. 10 times 1 will give you 10, or 100 times 1 will give you 100, for example. So any matrix multiplied by an identity matrix with the same order will give you exactly the same matrix again. This brings us to the first new term or calculation with matrices, and we call this the vector inner product. So if we have two vectors, remember a vector is a column or a row with numbers in it. It's a special type of matrix. So assume that we have two vectors, A and B, but they have the same number of elements. So let's say, like in this case, 3 elements in each. Then the inner product of A and B, let's call that S, would be A transpose. Remember where the columns become rows, so that the A will then change into rows if it was a column vector, times B, and that is also equal to B transpose times A. So where B, a column vector B in this case, will become a row multiplied by the column vector A. We are allowed to do that because they have the same number of elements, so the number of rows in A will be equal to the columns in B, or vice versa. And that gives you a numerical value, or a scalar, called, in this case we call it S. So if we look at our example, we have two column vectors A and B, 1, 2, 3 in this column and 4, 5, 6 in that column. So the vector inner product of A by B will be then A transpose, which means a row, or this column becoming a row, times that column, and we're allowed to do that. So that would be 1 times 4 plus 2 times 5 plus 3 times 6. Here you are. 4 plus 10 plus 18 gives you 32. So in this example, the vector inner product of A and B will be a numerical value 32. sometimes this is also called a dot product. This is not often used, but the vector inner product then is as we have described this. Similarly, we also get a vector outer product. So let's assume again that A and B are vectors. Then the outer product of A and B is a new matrix C. So the outer vector product of A and B will be A times B transpose, and that will give you C. So let's assume that A is a column vector with m elements and B is a column vector of n elements. You will notice now that the size or the number of elements of A and B differs. So obviously B transpose is a transpose of B, which makes B then a row vector. So in our calculation there, B then becomes a row vector, and now all of a sudden the outer product is a new matrix m by n. So you can see it takes on the m, the the columns of A, and n, the rows of n, as a new matrix. So in our example here, we have A, column vector with 2 elements, B, a column vector with 3 elements. So C, our outer product, would be A times transpose of B, and this will result in this new matrix C, which is then the outer product of A and B. This brings us to the next important part, namely dependency of vectors. Some vectors are actually dependent on other vectors or a factor of other vectors. So we talk about independent and dependent vectors. So obviously independent vectors will be 2 vectors or more vectors that's independent of each other. So there's no pattern of or a repeat or something which you can pick up from one vector to the next. The one vector is totally independent of the other. Versus dependent vectors, where a specific vector, and that could be a column or a row, is dependent on another one or more than one. So obviously the elements in this dependent vector, one can deduct that these elements were derived from the elements of other vectors. So let's then start talking about the linear combination of vectors. If one vector is equal to the sum of scalar multiples of another vector, we say that there is a linear combination. So, for example, if you have a vector A, but it's dependent from a linear combination or a sum of scalar multiples of another. So, let's say in this case A, which is a vector, is 2 times B plus 3 times C. So you can see that A is dependent on B and C in this case, but it's also there's a constant value that B and C is being multiplied with. So in this example, 2B then is a scalar multiple and 3C is a scalar multiple. B is a scalar, but it's a multiple. C is a scalar, but it's a multiple because it's been multiplied by a specific scalar. So A is linearly dependent on B and C. So let's look at this example. A is a column vector, in this case 11 and 16, but it's linearly dependent on B and C because it's basically B times 2 plus C times 3. So if we do this multiplication, and remember scalar with a the matrix, or in this case then a column vector, is 3 times 3, 3 times 4, 2 times 1, 2 times 2, and if we add the two new columns, we end up with this new column vector, which is 11, 16. So basically, A is dependent on B and C. So this is a linear dependency of A with B and C, and also with the multiplication of scalars in this case. Good. Here we have a few examples of row vectors, and I want you to pay attention to the fact that some of them are linearly dependent and some not. So let's look at the first example where we have linear dependency. So here we have a row vector C, but if you watch carefully, you will see that basically C is dependent on A and B. 1 plus 4 gives you 5, 2 plus 5 gives you 7, and 3 plus 6 gives you 9. So there's a linear dependency. C is linearly dependent on B and A. Similarly, A, in this case, is also linearly dependent on D. You can see that basically, obviously, they're both linearly dependent on each other. So 2 times A gives you D. 2 times 2, 2 times 1, I mean, gives you 2. 2 times 2 gives you 4. And 3 times 2 gives you 6. So basically, those two are linearly dependent. But in the same vein, or in a different vein, D, E, and F are linearly independent. There's no pattern of D, E, and F. You can't find any pattern here. It's not not one of them. If you add or subtract one from the other, the elements, or you multiply with a scalar, will result in any of the values in any of these three vectors, these column row vectors, D, E, and F. Dependency of rows and columns, like we have just done, will determine the rank of a matrix. So if you have a matrix, let's say an R by C matrix, and you think of that matrix as a set of row vectors, and each with C elements. So you have row vectors. Let's say it's a 5 by 3. So 5 rows by 3 columns. So you will have 3 elements per row. You can actually think of it as a set of C column vectors, the columns, each having R elements. That's your number of rows. So the rank of a matrix is defined as the maximum number of linearly independent column vectors in the matrix, or the maximum number of linearly independent row vectors in the matrix. And it's basically an equivalent. So if you have an R by C matrix and R is less than C, then the maximum rank of the matrix is R. If R is greater than C, then the maximum rank of the matrix will be C. So basically, any size of a matrix, as you describe it by number of rows and columns, the rank of the matrix will be maximized. It will be R by C if there's no linear dependency amongst any row or any column. If there's any linear dependency, any row or any column is dependent on another row or column, it will reduces the rank of the matrix. So let's say we have a 5 by 5 matrix, and none of those rows and none of those columns are linearly dependent on each other, then it's a full rank, and the rank of the matrix and the will then also be 5 by 5. But let's, for example, say that one row is dependent on another row, or one column is dependent on another column. Then it will not be a full rank. So the rank of the matrix will then only be a 4 by 4 and not a 5 by 5, as will be the case of a matrix with full rank. So when all the vectors in a matrix, as I've just said, are linearly independent, we talk about a matrix to be of full rank. So if we look at these two matrices, matrix A is a 2 by 3 matrix, and matrix B is a 3 by 3 matrix. Notice that row 2 of matrix A is a scalar multiple of row 1. 2 times 1 gives you 2, 2 times 2 gives you 4, and 3 times 2 gives you 6. So, therefore, row 1 and 2 are linearly dependent, and so matrix A has only one linearly independent row. So its rank is 1. So matrix A is not of full rank. If one looks at matrix B, and you find no pattern here that any of the rows or any of the columns are dependent on each other, and we can then say matrix B is of full rank. So the size of the matrix and the rank of the matrix will be exactly the same. The next very important calculation is the so-called determinant of a matrix, and that's a special number that can only be calculated from a square matrix. So only in the case of a square matrix one can calculate determinant of a matrix. So if you have a matrix, in this case let's call it matrix A, and it's a 2 by 2 matrix, 2 rows, 2 columns, the determinant of matrix A will be 3 times 6 minus 8 times 4. So 3 times 6 minus 8 times 4, that will be 18 minus 32, and it will give you a numerical value. And that is basically the determinant of a matrix. You will later on in this course we will tell you about the importance of knowing the determinant of a matrix, as this will determine whether it's possible to calculate the inverse of a matrix as well. And the calculation of inverses of matrices are extremely important in animal breeding. So this is a very simple example. It becomes a little bit more complicated where you have matrices more than 2 by 2. So here we have an example of a 3 by 3 matrix, and you will see that it's a fairly complicated way of how one calculate the determinant of this matrix. So there's a specific pattern in calculating that. I'm not going to handle that, and I'm not expecting from you to know exactly how this is being calculated, but if you use a spreadsheet or another method of calculation with your computer, and you should be able, you are supposed to be able to also calculate the determinant of a matrix using another means with your computer. And you can even do that with an ordinary spreadsheet like Excel or one of the other spreadsheets, and calculate the determinant of a matrix. Please also note how we denote determinant. It's basically two vertical lines on both sides of a specific um, alpha figure that we write down. Thank you. That was then part 3 of Matrix Algebra 101, part of the TLR course. Um, uh, some important factors that we did look into. We looked at an identity matrix. We also looked at the inner and outer vector multiplication, and then very important, the linear dependency or independency of row and column vectors, and then also the determinant of a matrix. Thank you very much. Part 4 will then follow after part 3.